It is very common for you to have to use Pythagoras in triangles or shapes that are not right-angled triangles. A very common trick is having to spot these right-angled triangles for yourself. Here on the left-hand side, I have got an isosceles triangle. I want to figure out how big these two sides are. I cannot use Pythagoras on the whole of this. What I need to do is I need to find a right-angled triangle. And the easiest way to do that is to split my shape down the middle. And that will give me a single right-angled triangle. That dashed line is actually the line of symmetry of that isosceles triangle. So it means if this side is x, the height of the triangle, the height up and down the way, is 35 centimetres, and the base has been cut in half. So this 100 centimetres will have been split in two, and that will have been split to 50 centimetres. I am now working with the type of diagram we've been working all the way through this topic. I've got a right-angled triangle, I know the two short sides, and x is one of my long sides. So x squared is 50 squared plus 35 squared. That will give me 3,725. X is the square root of that. So on my calculator I can type square root and use the answer button if I don't want to type all those digits in, and that will give me 61.032. So I'm going to round that to one decimal place, so that'll be 61.0 centimetres. The longest side of this right-angled triangle, 61 being bigger than both of these numbers. And because this is an isosceles triangle, the other side is also this. So both missing sides are 61.0. It's often a good idea just to write a short sentence with these types of questions, just to communicate your answer. Right, here I've got another isosceles triangle. I want to find the area of this triangular flag. Now, the area of a triangle is found by doing half base times height, where the base and height meet each other at a right angle. And the design of this flag is actually sort of giving away where the base and height are. The base is this line down here. The height is going to be this line up here. I know the base is going to be 30. But the height, well, I've got no idea. 39 is this slope. But I'm looking for this line here. But I've got a right-angled triangle I can pull out of my diagram. So I'm going to make a quick sketch. So I've just sort of copied the top half of the diagram. I don't need the full bit, I just need a right-angled triangle. Now this side here, that's the height of the triangle. Well, that is what I'm trying to find. This side here, well, the triangle has been split down the middle. So this 30 is going to get cut in half. So my 30 is going to be 15 there. H, the height, is one of the short sides because it's touching the right angle. So h squared is the big square, 39, minus the small square, 15. Right, typing that into my calculator gives me 1,296. H will be the square root of that. So again, square root answer will give me 36 exactly. So we're in one of these rare occasions where the number work has worked out nice and given us a whole answer. So I could put that onto my original diagram, 36. Now, I can actually answer the question now. The area is half base times height. So the area is going to be half of 30 times 36. So my area will come out as 540 square centimetres. Now, if this 36 was a horrible decimal number, I could have typed into my calculator here half times 30 times answer, and that would make sure I don't make any little rounding errors. It would use the exact value here. But we're lucky because 36 in our original calculation, it's a whole number. Okay, here now we've got two pictures of gardens. We've got new fencing is being erected around these gardens. Calculate the total length of fence needed to surround each garden. So what we've essentially been asked to find here is the perimeter. Now, to find the perimeter, we need to add up all the sides on each of our shapes. Garden 1, nice easy one to begin with. We've got a right angled triangle and we're trying to find the hypotenuse. So I'm going to mark that missing side as an x. X square will be 15 square plus 7 square. That gives me 274. So x, I have to unsquare that. I take the square root of my answer, and that gives me 16.55. So I'm going to round that to one decimal place, 16.6 metres. So the perimeter of garden 1 is 15 plus 7 plus my 16.6, and that will give me 38.6 metres. Make sure you actually say what it is you're figuring out. We're figuring out the perimeter, and I've just used a little 1 here to show it's for garden 1 because I'm dealing with two of them at the same time. Now, garden 2 is a little bit more difficult. We don't really have a triangle here at all. We've got a trapezium. You'll have dealt with problems like this when you'll have been dealing with area, in that you would split a shape like this into a rectangle and a triangle. And Pythagoras is exactly the same. If I drop a line down here, I'm going to have a right angle here, a right angle here, and most importantly, on the triangle, I'm also going to have a right angle. So it means the sketch I should really be making is this bit. I'm interested in the right angled triangle. Now, I know up and down the way, this is going to be 16 metres, because this line is 16 metres, so this line is 16 metres here. I know all the way along the top is 28, all the way along the bottom is 16, so the difference, 28 minus 16, will give me 12. So that's how big this bit I've cut off is. The sloped edge, this edge here, we don't know how long that is, so I'm going to label that y. I'm not using x again because I've used x over here. So y is the hypotenuse because it's not touching the right angle, so we're adding again. Y squared is 16 squared plus 12 squared, and that comes out with 400. So that's a nice number there, because the square root of 400 to find y is just 20. 20 lots of 20. You don't need to really notice this, but if I look at these two numbers and then the 20, you hopefully remember that a 3, 4, 5 triangle is what we call a Pythagorean triple. So this is a set of 3 numbers that give us a right angled triangle, ones without horrible decimals. 3, 4, 5, if we multiply 3 by 4, 4 by 4, and 5 by 4, we get this triangle. So it's just basically a big blown up version of that. You don't need to know that, but, well, it explains where some of our nice numbers come from. Our perimeter, so actually answering the question, perimeter of the second garden is going to be all four sides. So I've got the 28 along the top, plus the 16 down the side, plus the 16 along the bottom, plus the 20. Totalling all of that up gives us an answer of 80 metres. Okay, final example I'm going to do here. This is the trickiest one I'm going to look at. And to be honest, maybe only a handful of you will look at this. Pythagoras can help us with three-dimensional problems. This problem here is pretty much something you would find in a National 5 exam. So don't worry about it if this is trickier than you think you're going to manage, okay? You just won't work on this just now. Pythagoras is one way to do it. There is another way involving something called vectors, something you may have seen briefly in first year, but I'm going to show you how we can use Pythagoras. So here, a tree is located in the corner of a rectangular field. We've got this diagram here. The field is 10 long by 9 wide, so 10 by 9, and the tree is 9 metres tall, 4 metres tall, sorry. Calculate the length AE. So AE is this line here, there, up to the top of the tree. Now, I'm actually going to draw in a couple extra lines. I'm actually going to draw in the height of the tree. So that's there, going from the corner of the field up to the top. There are a few right angles I can fill in here as well. This is a rectangular field, so it's been sort of drawn at an angle here. So these are all right angles. There is one more right angle, and it is formed here. The tree is growing straight up and down the way. So this is a right angle here. The tree is going to be at a right angle with the ground. So if I draw a line going out in any direction from the base of the tree, I'm going to have a right angle. The direction I'm most interested in, though, is this direction I've got drawn in here. Because I am going to draw a line from the tree straight across here. I've now got two right-angled triangles. This one that I've coloured in yellow, I know one side is 9 metres, and I know this here is going to be 10 metres. Because I know two of these three sides, I can now figure out this side. Now, why would I want to figure out this side? Well, the triangle I've just coloured in green there is the one that I actually want to work with. This line is the one I need to know. Okay, this is one I've been asked to find out. I know this is 4, but the only way to figure out this is if I know the 4 and the diagonal of the field. So I'm going to have to work with the yellow triangle to get this, which will allow me to then work with the green triangle. So the sketches I'm going to draw this yellow one, then I'm going to draw this green one. So there's my yellow right angle triangle, ADC. I know that is 10 metres, I know that's 9 metres, and I want to find the missing side. So I can say the missing side, let's just use the label AC. AC squared is 10 squared plus 9 squared. And that'll give me 181. AC will be the square root of that. My calculator gives me 13.453. I don't need to even bother rounding this. I'm just going to write 453 ... because this isn't us finished the problem. This is us sort of halfway through. I'm now going to draw the green triangle. So there he goes. I know this is 4, going from C to E. This is A down here, so just copying it from the diagram on the left. AC, I've just figured out, that's 13.453. metres. AE is the hypotenuse. So AE squared equals this big long number squared. So I'm going to use my answer button to type that in. Plus 4 squared. And that equals 197. Now, an alternative way of typing all of this in is to actually use this previous step. We know 13.453 squared, well, it's going to undo this step. It's going to take us back to 181. So we could just write this as 181 plus 4 squared, and it'll still give us 197. All that remains to be done now is to actually answer our question. So AE is going to be the square root of 197. So the square root of my answer gives me 14.035, and because this is my final answer, I can round that off. So at 1 decimal place, 03 will round to just 0, giving me a final measurement of 14.0 metres. So the tasks that you're being asked to do, you will be asked to do 2 of these 4 sets of problems. Problems 1 has 4 little sections in it, and you are just basically practicing your right-angled Pythagoras. So skill 1 and skill 2 are finding missing sides. So you draw a quick sketch and do your working beside it. Stretch 1 and stretch 2 have got some problem solving ones. But again, with these you should be trying to draw a sketch of a right-angled triangle to help you. Problems 2, this is similar to the garden or the area shapes. Find the length of the diagonals. Remember, diagonals are going corner to corner. So that will cut these rectangles into right-angled triangles. Find the perimeter and area. Well, you need the length and the breadth. We know a diagonal, so we've got a wee right-angled triangle there already. We've got a wee right-angled triangle there and there. 3, that is almost identical to the garden one we've done. You've got 3 triangles. You need to find their perimeter. Area was also covered in this video, so the half base times height. Tasks 3 and 4 are increasingly difficult exercises. There is a little bit of crossover between them, but task 3 is basically this 2-dimensional type problems. Task 4 gets stuck in to lots of 3D problems there. With each of these, especially these and these bottom ones here, you'll be wanting to draw lots of sketches of just the right-angled triangles you're working with.